So, you've built this amazing AI model. That's the first step. But how do you really know if it's working? I mean, we always hear this one magic number, right? Accuracy. It's supposed to tell us the whole story. But here's the thing. What if that number is actually lying to you? Well, today we're going to pull back the curtain and look at a tool that shows us what's really going on.
All right, let's just jump right into it. I want to ask you a question. Imagine you've got an AI model and you're told it's 80% accurate. So, what's your first thought? Is that good? I mean, would you bet on it? Would you feel confident rolling that out into the real world?
On the surface, 80%, it sounds pretty good, doesn't it? I mean, that's a B minus, maybe a solid B in school. If you have a model that's supposed to spot a disease, getting it right 8 times out of 10 feels okay. But this is exactly where that simple number starts to get really, really dangerous. Okay, but what if I told you that buried inside that pretty good 80% score is this little detail? 10 patients, people who are actually sick, were told they're totally fine. Go home, you're healthy. All of a sudden, that 80% doesn't sound so good anymore, right? The cost of being wrong, well, it changes the entire game. And that right there is the huge problem with just looking at one number for accuracy. It's kind of like judging a book by its cover. Sure, you get a vague idea, but you miss the whole plot, all the characters, the entire story. It just doesn't tell you anything about the kind of mistakes your model is making. And this is exactly why it fails. You see, accuracy just lumps all the mistakes together into one big pile. It treats every single error as if it's exactly the same. But come on, we know that's not true, right? A spam email slipping into your inbox is annoying, sure, but it is not the same as an AI missing a serious medical diagnosis. By just counting up the total wins, accuracy totally hides the context. It lets a model look good, even when it's failing at the one job that matters most. So, if accuracy is the problem, what's the solution? How do we get the full picture? How do we, pop the hood and see what's really happening with the engine? Well, we need a better tool. And that tool is called the confusion matrix. And trust me, its whole job is to stop all the confusion and finally tell us the truth. So what is this thing? At its core, a confusion matrix is just a simple table. That's it. It puts the model's predictions on one side and compares them to what actually happened in the real world. So we're not just counting up the mistakes anymore. We're sorting them into different buckets to see exactly what kind of mistakes they were. And that is where things get interesting. Okay, so let's take a look at the basic layout. It's just a simple 2x2 grid. The columns up top, that's what the AI predicted. It either said, yep, disease, or nope, no disease. And the rows on the side, that's the actual truth. That's what a doctor confirmed. And where those rows and columns cross over, that gives us 4 little boxes, 4 possible outcomes. All right, let's dive into what each of these 4 boxes actually means. We'll stick with our medical example to make it super clear. First up, we've got the true positive. This is the big win. It's when the model says this person has the disease and it's right. The patient was actually sick. A perfect match. We want a lot of these. Then you've got the true negative. This is the other kind of win. The model says this person is healthy. And guess what? They are. Another correct prediction. So far, so good. Okay, now we get to the mistakes. First is the false positive. You can think of this as a false alarm. The model screams, disease, but the person is actually perfectly healthy. Now, this isn't great, right? It causes a lot of stress, maybe some unnecessary tests, but in the grand scheme of things, it's usually the less dangerous of the 2 types of errors. And that brings us to the one we really, really worry about in this case, the false negative. This is when the model says, you're fine, no disease here, but the person is actually sick. This is the disaster scenario we talked about at the beginning. This is the person who gets sent home thinking they're healthy when they desperately need treatment. This is the mistake that can have huge consequences. So you can see this really drives home the main point here. Not all mistakes are created equal. A false alarm is a problem, for sure, but a missed case, that can be a tragedy. So let's go back to our original example with 100 patients and see how the numbers actually stack up. Okay, check this out. Now we can finally see the whole story behind that 80% accuracy score. See the 30 true positives and the 50 true negatives? Add those up. That's our 80 correct predictions. But look, now the mistakes aren't hidden. We can clearly see the 10 false positives, and there they are, those 10 really dangerous false negatives. Everything is out in the open now. And this is really the whole point.
The confusion matrix shows you exactly how all the predictions are spread out. You're not just getting a single blurry number anymore. Instead of one vague accuracy score, you get 4 super specific, super meaningful numbers that tell you the complete story. Okay, so now that we have these 4 numbers, what do we do with them? Well, we can finally graduate from plain old accuracy. This matrix lets us calculate much smarter measurements, metrics that tell us what we actually care about when it comes to the model's performance. Let's start with a metric called precision. Basically, precision answers this question. When the model did predict disease, how often was it correct? Think about it like this. You want high precision when a false positive is a really big deal. The classic example is a spam filter. You want it to be very precise so it doesn't just start throwing important emails from your boss into the junk folder. Now, the flip side of that coin is recall. Recall asks a totally different question. It asks, of all the people who were actually sick out there, how many did our model manage to find? This is the metric for our medical example. We absolutely cannot afford to miss sick people, so we need to maximize our recall. We have to find every single case we possibly can. So here they are, side by side. Precision is all about avoiding those false alarms. Recall is all about not missing the real thing. And here's the really important part. These two are often fighting each other. It's a trade-off. If you try to make your model super precise, let's say you tell it to only flag something if it's 100% certain, you'll probably miss a bunch of actual cases. Your recall will go down. The real art is figuring out the right balance for whatever you're trying to do. So, there you have it. We've gone from one simple and frankly misleading number to a much richer, smarter way of understanding how an AI is actually performing. So I'll just leave you with this one question. The next time you read a headline that says some new AI has 99% accuracy, what's the first thing you're going to ask? Because now you know, sometimes the most important part of the story is hidden in that other 1%.